Now, this is the reason to do the mean value theorem is that you use it to prove stuff about when you can use a derivative to figure out where a function is increasing or decreasing. So, and most of these things should seem kind of intuitive to you already. If a derivative is positive, then the function is increasing. You think, okay, if the derivative is positive, the slopes of my tangent lines are positive, right? And since the tangent lines have the same direction as the curve, positive slope kind of means going up, right? So you think, okay, here I've got like a, say, a parabola. When the derivative is positive, your function is increasing. That idea makes sense? And if the derivative is negative, the function is decreasing. But to formally prove it, you have to use the mean value theorem. So I'll show you one. We're just going to prove A. So to show increasing, if you have x1 is less than x2, then what's the relationship between f of x1 and f of x2? If your function's increasing, who's bigger? The first y or the second y? The second y. So this, which thing does the inequality eat in that second thing? Does it open this? Does it go this way or does it go the other way? It goes that way, right? Yeah, okay. I mean, if I was saying, what if I changed this to decreasing? Same thing, if x1 is less than x2, your y's have to go down. How would that change this? It'd go the other way. I think that's what Mary Kate is saying when she's pointing the other direction, right? Yes. Does that make sense, though? Okay.
You keep the first one the same.
Yeah, well, because what this says is if your first x is less than your second x, your first y is less than your second y. That's how you formally say going up, right? And to formally say going down, if your first x is less than your second x, then the y for the first one was bigger. Okay. All right, so we're just talking about increasing. Now we suppose f prime of x is, oh, I hate it when I don't have my eraser. Suppose f prime of x is bigger than 0. That's the whole if we have that on an interval with x1 and x2 in it. Okay. By the mean value theorem, then f prime of x will have to equal f of x2 minus f of x1 over x2 minus x1. When you can apply the mean value theorem because the derivative exists and therefore the function is continuous and differentiable, that's kind of a technicality, but you know, this is baby proofs. But you at least agree with the whole, it's just instead of a's and b's, it's x2s and x1s, right? Nothing's different. Or f prime of x times x2 minus x1 is equal to f of x2 minus f of x1, right? Okay, I'm just going to rewrite that as f of x2 minus f of x1 is equal to f prime of x times x2 minus x1. So we know f prime of x is bigger than 0, right? Because we said that, suppose that was true. And how about x2 minus x1? How do you know that's positive? Look at the, I mean, I guess you did assume that x1 was smaller than x2, right? And if x1 is smaller than x2, then taking the bigger x minus the smaller x is going to yield a positive number, right? This is also positive. So that means you got something positive, sometimes something positive, which makes a positive. So f of x2 minus f of x1 has to be bigger than 0 because the right side is positive. Or you know that f of x2 is bigger than f of x1 by adding the f of x1 over. And that means increasing, right? You're just going to have to use the result. Now, if we were showing decreasing, here's how that would have changed. This thing would have been f prime of x was less than 0, so that the derivative is negative. That would have changed this thing to f prime of x less than 0. Would it have changed this? I don't think so, right? And then you would have had a, if f prime is less than 0, that's a negative, right? Times a positive. This would have changed to less than 0. Other than that's the exact same thing. But you would have known that the stuff on the right side was negative, therefore the left side had to also be negative. Mostly we're just gonna use this. You're not going to prove it again, but that's the reason why is mean value theorem. Okay. And one more thing called the first derivative test. So suppose you have a critical number. If the derivative changes from positive to negative at your critical number, then f has a max. So the picture of that is something like this. Derivative positive, derivative negative. That means critical number is a max. Local max. You don't know about global max. If it's the other way, if the derivative changes from negative to positive, that means you were decreasing then increasing, right? That means a min. And then if f prime does not change sign, like say cubic, right? Derivative positive, it's one of those no numbers, not a max or a min. Okay? All right, so let's figure out where a function is increasing and decreasing, then find the local maxes and local mins. So to figure out increasing and decreasing, you look at the derivative. So what is the derivative? Yep, 12x cubed minus 12x squared minus 24x. And you want to figure out where this is positive and negative. You did something a lot like this in pre-calculus. You made sign charts. We're going to do the same thing. It's just the sign chart's going to be for f prime instead of for f. So first, set it equal to 0.
Can you pull a 12 out of that?
You can pull, yes.
X. Make it smaller.
And you can pull it in x, yes. So 12x times x squared minus x minus 2. And then how does this stuff factor? Yep. And so the zeros are 0, 2, and -1. Okay, now make a number line. And when you're testing for signs, you always plot those zeros on the number line. So you've got -1, 0, and 2. We're testing the sign of f prime. And so I would suggest color coding, circling, finding some way to identify what's your test numbers and what are your actual critical numbers. So what's a good test number to the left of -1? -2. And the easiest thing to do is to plug it into the factored form and then just look at what the sign is going to be. Is it going to be positive or negative in the end? look at it factor by factor. So the first factor will be negative, the second factor will be, and the third factor will be negative. So overall, you're negative on that subinterval, which means what's your function doing there? Decreasing, going down, yep. What's a good test number between -1 and 0? -0.5, sure. So first factor, negative. Second factor, negative. How about the third factor? So overall, you're positive.
It's coming down and swooping up, that's a negative?
So
Or
it
that-
goes
that's
down,
zero.
sweeps up, yep, exactly. How about between 0 and 2? 1, sure. All right, that'd be a plus, minus, plus, right? So overall minus, so it means it goes up, swoops down again, right? And then past 2, say 3, I think you're plus, plus, plus. So it does this kind of thing. I mean, ish. Specifically how far up or how far down depends on what you get when you plug numbers in your function. Like it's a general shape. It goes down, it goes up, it goes down, it goes up.
If it didn't do that, I'd be confused.
Well, sometimes it could like level out like a cubic does and then go up again, just like x cubed does. Okay, so you need to actually tell me where the function's doing what. So f, the number line is your work, not your answer. F is increasing where? And 2 to infinity. And the reasoning is since f prime is positive. F is decreasing where? Yep. And, and the reasoning is there is that since the derivative is less than 0. So there's the increase and decrease thing. I'll let you pause and write that. Okay. Is everyone okay with the whole increase-decrease thing? All right, so on my number line, I like to draw some stuff to help me a little bit. So if I decrease then increase, I've got something like this happening with my original function, right? If I go down then go back up. Versus if I go up and go back down, I've got something like that happening with my original function, right? And here I've got something, a down and an up, right? So where are the local minima? At x equals -1 and at x equals 2. When you plug those numbers in, I'm pretty sure with WebAssign you'll actually have to plug them in. You get, when you plug in -1, you get 0, and you plug in 2, you get -3. Is there a local maximum? And when you plug in 0, you get out 5. So I'll try to be specific when I want ordered pairs or when I want x only. Like if I want x only, I'm going to say x only because it just becomes too tedious to plug stuff in. Does that make sense? But WebAssign, you have calculators and stuff where you can get help with that stuff or just check that you're right. I mean, with help make the arithmetic less awful. Okay. Example 2 is not as easy as it looks, at least at first glance. Okay. So, is this a graph of the original function? No, it's a graph of the derivative, okay? So let's do it, now we're just given a graph instead of an equation. So let's just do it the same way we did in the previous one. Let's make a number line, and we'll look and see there's gonna be a relationship between the number line and between the picture. And hopefully if you can see that, you can do this faster, okay? So the first thing we did was we found the zeros. Right, that was step one, was to figure out where does f prime of x equal 0. We plotted those things on our number line, right? So this derivative will be 0 whenever it crosses the x-axis. Does that make sense? So where is the derivative 0? -2. Mm-hmm. 0,
4,
2, and
4.
4, okay? Sine f prime.
Does it actually cross the two?
It touches but doesn't cross. Yep.
Oh, that's zero.
Yep, but it's still a 0. It's still equal to 0. Okay, now if I picked a number on this interval and plugged it into my derivative, would the answer be a negative or positive number? Nope, you take a number, you plug it into f prime. If I found f prime of -3, it'd be down there. So what is the sign of f prime of -3? Negative or positive? Negative, because it's below the x-axis.
The y value is below
The y value is below the x-axis, yep. What if I tested -1? What would the y value be of f prime when you tested -1? Positive. And then negative and negative, and then positive. Testing in f prime means find the y value of f prime. Does that make sense? Okay. So on what intervals is f increasing? On what intervals is f decreasing? So look at your sign chart. When is f increasing?
Go 2, 0,
Uh-huh.
4, whatever.
And then we're just going to assume this goes forever, so 4 to infinity. Okay. Notice that's the same place the graph of f prime is above the x-axis. Do you see what I'm saying?
The what?
Okay, these intervals that we found is the same place where the graph -2 to 0, that's that part right there, right? 4 to infinity, where the graph of f prime is above the x-axis. Okay, where is it decreasing? Mm-hmm. Also negative infinity to -2. Does that make sense? And technically speaking, you have to leave out 2. So you have to say 0 to 2, union 2 to infinity. And that's a technicality because at 2, the derivative is 0, not negative. It's an in-between number. So it neither increases nor decreases at that one point. Yes?
Wouldn't it just be 4 to infinity?
Wait. I boo-booed. -2 to should have been that. Yep. And notice that's where how does that relate to the graph of f prime?
It's below x.
Mm-hmm. It is easier that way, right? So that's my point, was to make it so that you could do it that way. This graphs the slopes, right? If the slopes are positive, i.e. above the x-axis, your function was increasing. If the slopes are negative, below the x-axis, your function is decreasing. So that you can do all the rest of them that way, okay? But this is just to explain how this picture relates to what we did before. Okay. At what values does f have a local max or local min? So this was minus plus, right? So what happens at -2, a max or a min? Mm-hmm. went from decrease to increase. How about 0 to 1? How about you went plus on this side? What was the derivative sign on their side? Negative. So if you go from positive to negative, you go up and down, that means you have a, Is there anything at 2? Nope. Not at x equals 2. How about x equals 4? It's a min. Could you find the y values there if I wanted you to? You'd need the original function, wouldn't you?
Yeah,
And you don't know what it is.
it's harder when you have the derivative.
It is a little bit hard. Yes, it is a little bit harder when you have the derivative, for sure. Okay, one more with trig, just for kicks. Find the local max and min of this function on this interval. So to find local maxes and mins, you're just going to make that sign chart. So first thing is figure out where the derivative is 0. So it's going to be a 1 plus 2 cosine x, right? So 0 equals 1 plus 2 cosine x. Cosine x equals
Negative one.
-1 half.
Oh,
Okay. So when is the cosine negative? What quadrants? 2 and 3, great. And is it this one or is it that one? It's the first one, isn't it? So x is equal to pi thirds, and this one down there is 4 pi thirds. Great. Is that okay?
2 pi thirds.
Yes, it is. Okay, let's make our sign chart. And we have 0 to 2 pi. Thank God, we have like an infinite number of intervals. That'd be a really big pain, right? So we have 2 pi thirds and 4 pi thirds. Those are our places where the derivative is 0, right? Our critical numbers. Now pick good test numbers. So it does actually work to test these endpoints as long as the derivative isn't 0 at those endpoints. But the good candidates for test numbers in your derivative are the super, super easy ones to plug in. Does that make sense? The easiest numbers to plug in are the whole or half pies. Does that make sense? If they're not an option, the quarter pies are the next easiest option, right? Because you can't mess up who's who as long as you can keep track of your signs. So if you were going to test 0 in this derivative, what are you going to get? Exactly. If you plug 0 into there, are you going to get what number? What's cosine of 0?
1.
Is 1. So what's 1? That'd be 3, i.e. positive, right? If you tested pi halves, would you get the same conclusion about the sign? When you plug in pi halves into the derivative, you'd get 1 out, right? Which is still positive. Okay. What's a good test number between 2 pi thirds and 4 pi thirds? Pi. And when you plug in pi, what's cosine of pi?
-1.
So that'd be 1 minus 2, which gives you a
Negative.
negative number. Plugging in 2 pi, same as plugging in 0, right? So it'll be positive again.
And when we get, you wouldn't have to see if there's more than one sign change between those.
No, because if there had been another sign change between them, you would have had another 0. Does that make sense? So that once you have the zeros, there can be no more sign changes or you introduce more zeros. Okay, so where is there a local max? Which one of those is the local max? 2 pi thirds or 4 pi thirds? Local max at x equals 2 pi thirds. Let's just find the y there. F of 2 pi thirds will equal 2 pi thirds plus 2 sine of 2 pi thirds. So what's sine of 2 pi thirds going to be? Square root 3 over 2, which will become root 3 when you cancel that 2. So 2 pi thirds plus root 3. There's a local max.
That's 2 pi thirds?
That's at 2 pi thirds, yep.
It looks like 8 pi thirds.
That's because I boo-booed. I should just erase. Okay, how about at 4 pi thirds? Is it a min or a max? Min. And then plugging in 4 pi thirds. That will be 4 pi thirds plus 2 sine of 4 pi thirds. So that'll be 4 pi thirds. What is the sign, positive or negative, of sine of 4 pi thirds? Negative, right? So that'd be just minus root 3. Okay. Is everyone all right with how to find local maxes and mins and intervals of increase, decrease? It's not very hard, right? The mean value theorem is definitely harder. Okay. Now, another thing that matters is the manner in which a function increases. So you have to draw this, but I'm going to show you something. There are two functions increasing, okay? I'm going to draw two functions that are increasing. Okay, there's that function that's increasing, and here's this function that's increasing. So if this is time and this is how much money you have, which function do you want to be your investment?
I want the first one.
The first one, because it's increasing more quickly, right? This, you say this is increasing at an increasing rate. Does that idea make sense? It's increasing, and how quickly it's increasing is also increasing. Another way of saying that is that its velocity and acceleration are positive. You're increasing and you're accelerating. Does that make sense? This one is increasing at a decreasing rate. This is kind of like the national deficit, actually. Like when they say things, they actually are using this kind of language. They'll say, okay, well, the national debt is increasing, right? But how quickly it's increasing is decreasing. Does that idea make sense? Like it's still going up, but how quickly it's going up is going down.
Population growth as well.
Population growth is still the first one.
I think they said it was tapering off.
Yeah, the rate's slowing slightly, but it's still exponential. So I think that the rate of exponential growth is lower, but it's still, and because it's still exponential growth, I don't think so.
I think I remember reading in 2012, they said the rate of population increased was the first time that it didn't go up.
In the US.
This graph is above all of its tangent lines, concave up. This graph, if you look at its tangent lines, what's true about it and its tangent lines? It's below them. Okay, let's move it on, okay? Because once again, something I can't verify right now except for Jesse knows. So if the graph of f lies above, so what this shape is called is it's called concavity. If the graph of f lies above all of its tangent lines on an interval, this is called concave up. So look back at that picture, that's the technical definition. And a point P on a curve is called an inflection point if the function is continuous there and the curve changes from concave up to concave down. Now I had a student once who had a great sort of like rhyme for this. It was concave up like a cup. Like looks like a cup, right? Concave down
Like a frown?
Yes. In some sense, that helps a little bit, right? Concave up means sort of opening upwards. Concave down means opening down. I think of it as an upside down or right side up umbrella is my personal way I did it, but I thought that was kind of cute. And an inflection point is when you change concavity. Those are harder to see than maxes and mins. They're kind of subtle. But like x cubed has an inflection point. Do you see how it sort of opens down and then at that point opens up again? So that's what would be, and they're harder to find just a spot in a picture, but an inflection point is a change in concavity. Okay, so this is a graph, it should have said of the original function. So tell me, where is this function concave up? I'm going to use CU for concave up. I'm going to use CD for concave down. So where is it concave up or opening upwards? On what intervals? B to C, yep. Where else? D to E, but it looks a little bit like a C. And then how about where else? Uh-huh. Okay, how about concave down?
A to B,
Uh-huh.
C to D,
And
P to Q.
P to Q. Okay. I'm going to use IP for inflection point just because, you know, like, it's just too much writing otherwise. So for you to have an inflection point, the concavity has to change. So does the concavity change at B? I think it does. It goes from down to up. It's kind of opening downwards, then opening upwards. It doesn't, like, it's not a max or min. It does the concavity change. So at x equals B. How about C? Does the concavity change? Like the way it opens? It was opening up, and after C, it opens down. So B, sure. C, sure. How about D? Yep, more obvious there. Does the concavity change at E? Nope. Does it change at P? Yes.
So it doesn't matter how little it changes.
Nope, but then the changes are going to look quite subtle. Yep.
B and C are quite subtle.
B and C are quite subtle, but you know, if you said I'm concave down in one interval, concave up on the next. So since they're sort of subtle to see in a picture, we want a way to find them exactly without having to rely on our guessing abilities. Does that make sense?
Would that have something to do with second
It has to do with the second derivative. Yep. And the hint about acceleration is kind of the hint. So remember that this is a concave up guy, right? So I said the acceleration was positive, right? Which is the second derivative. And that's kind of the hint. If the second derivative is positive, the graph of f is concave up. Okay? You can be concave up and increasing. You can also be concave up and decreasing. That's possible. And if the second derivative is negative, the graph is concave down. And part C, I'll add, is that if f prime prime changes sign, we'll say at x equals C, then there is an inflection point at x equals C. I don't know, gosh, crap. So inflection points occur where the second derivative is equal to 0 and the second derivative changes sign. If the second derivative doesn't change sign, there's not a max or min there. Kind of like if the first derivative didn't change sign. Said the wrong thing, didn't I? If the second derivative doesn't change sign, there's not an inflection point. If the first derivative doesn't change sign, there's not a max or a min. Okay. All right. So let's actually do this for a specific function. So first, figure out where the function's increasing or decreasing. What do you use for this? The first derivative. So that's gonna be 6x squared minus 6x minus 12. Set it equal to 0, take out the 6. Ooh, one thing to be a bit careful about, don't divide by that number, that 6. It doesn't matter if it's positive 6, but if it were negative 6, it'll change the result of all your conclusions. And I'll talk about that when we finish this part. So that'd be 6, x minus 2, x plus 1. Where is that equal to 0? 2, negative 1. Okay, let's pick some test points. If we tested, say, negative 2, what would the result be? Yes, it'd be a negative times a negative, which makes a positive. If you tested 0, what would the result be? It'd be a negative times a positive, which makes a negative.
And the next one's gonna be positive.
Yep. It doesn't always flip-flop, it just often does. So
Well, this is an x cubed graph. The other thing was negative, then that wouldn't.
some x cubed graphs will have no change at a place where the derivative is 0, like x cubed itself.
But then the graph would be going up and, from negative infinity and then going down towards infinity. It doesn't make sense for an x cubed graph.
Okay, so anyhow, now here's what I wanted to point out. What if this had been a negative 6? What would that have done to all of your sign analysis? If this were a negative 6, and then this were a negative 6, right? What would this have been? Negative. What would this have been? And this would have been negative. So be careful about stuff like that, okay? The positive thing doesn't affect any bits, right? It keeps this up, but just watch it. If that were a negative number, it could change stuff. So just be really careful to not, I wouldn't divide by constants for that reason. Okay. Roll to the end. So where is f increasing? So f increasing on negative infinity to negative 1, and one more place. 2 to infinity, and f is decreasing. So it'll do something like where it goes up, goes down, and then goes up again, right? Okay. So local max, local min. So who's the local max? At negative 1 or at
Negative 1.
So f of negative 1, which is negative 2 minus 3 plus 12. So what's that? 7? That's the local max. F of 2, which is 16 minus 12 minus 24. Negative 20, is that what you said? That's the local min. You guys buy that? Did I add right? Okay. What's next? Okay. Which means look at the, what? The second derivative. So f prime of x was equal to 6x squared minus 6x minus 12, right? So what's the second derivative? And we're going to figure out where that thing's equal to 0, which you can solve sort of the traditional add 6, divide by 12 way, or you can factor out a 6. So where's that equal to 0? Just one place, 1/2. And now we're looking at f prime prime's sign. Okay, so if you plug in a number prior to 1/2, say 0, is the result positive, in f prime prime, is the result positive or negative?
It's
It's
positive.
negative. Definitely negative.
2 times 0 is 2.
No, 2 times 0 is definitely 0.
Right.
It's okay. If you plug in 1, 2 times 1 is 2, then we're going to have positive, right? So f is concave up on what interval? Mm-hmm. And f is concave down on any 2 1/2, yep. Is there an inflection point? Is there a place where the concavity changes? Uh-huh. Yep, f of 1/2. That's going to be our inflection point. And oh my God, plug in fractions. Oh goodness, what's 1/2 cubed? 1/8. What's 1/2 squared? 1/4. Minus 12 times 1/2 is going to give us 6. Okay, it's not that bad. So I think that's 1/4 minus 3/4 minus 6. You buy that? So negative 1/2 minus 6 is negative 6.5 or 13/2. And we're not doing this quite yet, but let me add in one more thing to this. Let's sketch a graph. Okay. You can make your x and y axes have different units. So where were the important points? Like, where were the critical numbers? What were the x values of them?
Negative 1 and 2.
So negative 1 and 2. What was the y value at negative 1? 7. So I'm just going to count by, and the other one was negative 20, so I'm going to count by 10. So 10, 20, 10, 20, both negative. So negative 1, 7-ish is, right there approximately. You plugged in 2 and you got minus 20, so you're down there. So that's a critical number, critical number. When you plugged in 1/2, you got negative 6.5, so you're somewhere there-ish, right? What does your function do before it gets to negative 1? Is it increasing or decreasing? From negative infinity to negative 1, it's increasing, so it has to go up to negative 1. And is it concave down or concave up?
Yeah.
Down, yep. Down. And then when does it become, and then what happens from negative 1 to that 2? What does it do? Look at your part A. F is doing what from negative 1 to 2? Decreasing, so it goes down, but what does it have to do with that little dot in the middle? It was concave down, and then it becomes concave up. A little subtle. And what does it do from 2 on? It goes up. So there you go. And that's about what the picture looks like. Which is a lot better than what you did if you did graphed in pre-calculus, right? I mean, like, you usually tell where those points are now, as opposed to having to use like a calculator to figure them out or something like that. So. Is that all right? Okay. One thing we'll do later on in this unit is we'll do more graphing. So, okay. So the graph of the second derivative is shown. So find the inflection points. I'm also going to want you to tell me where the function is. Where is f concave up? Where is f concave down? Okay, so f is concave up if f prime prime is what? Positive or negative? Positive. Okay. So F is concave up on, where in this picture is the second derivative positive? This is the graph of the second derivative. It's positive if it's above the x-axis. That'd be from 1 to 4 and 4 to 7. Because you cut 4 out because the derivative is 0 there. So F is concave down if the second derivative is negative. This is a graph of the second derivative, and let's assume 0 and 8 are asymptotes. Okay, you could also assume that they're infinities. It's hard to tell. I mean, it's completely ambiguous. So F is concave down on what intervals? Sure, negative infinity to 1 and union 7 to positive infinity, right? Or if we assume 0 and 8 were asymptotes, it really would have been 0 to 1 and 7 to 8. Does that make sense? But that's a technicality, and I wouldn't really judge you if you did it both ways, because it isn't clear if that graph is going to go past the, y-axis or not. It's totally unclear. Okay, that's a little bit like the whole increasing, decreasing thing, isn't it? Okay. Now, inflection points at x equals 1 and 7. And the kicker is not x equals 4, because the function was concave up and stayed concave up. Does that make sense? Even though the second derivative was 0, there wasn't an inflection point there. It wasn't enough. There was no sign change.
Because it's the F prime prime.
Yeah, F prime prime sign would have been negative, positive, positive, negative. And there's no sign change at 4.
Could you argue for 3 and 5?
That's what I was thinking. Because
No, 3 and 5 would be true if this were a graph of F. Does that make sense? So, yeah, it's different. If you're given a graph of F versus a graph of F prime prime. Yeah, so if it were F, then yes, those would be the inflection points. But it's not F, it's F prime prime. It does make it hard. Okay, now another thing that the second derivative is useful for is determining if something is a max or a min. So it's kind of a cool test. If your first derivative is 0 and the second derivative is positive, then F has a minimum at that point. So think about what these things mean. If the first derivative is 0, you have to have a min or you have to have a zeroing out point, right? If the second derivative is positive, that means you're concave up. Think what that looks like. You'll have a place where it's 0, your first derivative is 0, and you're concave up. That means that you have a min at that point, right? If your first derivative is 0 and the second derivative is negative, that means you're concave down. Therefore, at that place where the derivative was 0, you have to have a max. Does that make sense? What freaks people out is they think, oh, positive second derivative means min, negative means max, and they get all whacked out about the signs. They get messed up with positive being min and negative being max. Do you see what I'm saying? If you think about what second derivative means in terms of positive, negative, and just draw a picture, I think it's pretty obvious. Okay, so we're going to do, that second derivative test is only useful if taking the second derivative is easy. If taking the second derivative is hard, you just make a number line, you don't want to use it. We will use it a lot in a later applied section in this chapter. So for now you have to know it, and then we'll use it a lot more later. So let's just do one using both tests. And one thing that I forgot to add is that if the second derivative is equal to 0, then the test fails. And then you must use the first derivative test. And the first derivative test is where we use the number line and just saw, did it change from positive to negative? Or the first derivative change from negative to positive? Okay, so if we're going to use the first derivative test, first find the first derivative, which is what? Set it equal to 0. Take out a 4x. Take out a 4x squared even, right? Dane agrees? I think you need your hot pocket. X minus 3. Oh. Then test the sign of f prime. So what are my zeros?
They are 0 and 3.
Okay, let's test a number to the left of 0. Let's test -1. Is the result, when you test -1 in f prime, positive or negative?
It's negative.
It's negative. Okay, let's test 1. Is the result positive or negative?
Negative.
Negative again. Test 4.
That would be positive.
Would be positive. So f of 3, which is equal to 81 minus 4 times 27, hugeness. F of 3 is 81 minus 108, I think. So what's that?
A negative number.
Well, you can do 108 minus 81, can't you? But negative, right? Okay. So is it going to be a max or a min? Decrease, increase. It's a min. And how about f of 0? Is that a max or a min? It goes from, the first derivative goes from negative to negative. So the function goes down, then goes down again. So is that a max or a min?
No.
That's a neither. So if you look at this picture, it's going to go decreasing, level off, decreasing again, versus decrease then increase. Just like x cubed. Well, that'd be negative x cubed, but you know, something similar to x cubed. Okay, so that's using the first derivative test. That means make the number line. But this function will not have a maximum. So it's going to start off decreasing, level off, decrease some more. It looks something like this. There is no local max. Just doesn't have one.
Where's the maximum?
Now, to use the second derivative test, first thing you do is you set f prime of x, which is 4x cubed minus 12x squared, equal to 0, which we did before, right? 4x squared times x minus 3, and we found x equals 0 and 3, right? So those are your critical numbers. So that's step 1, is find the critical numbers. Step 2 is to test the critical numbers in f prime prime of x. And what's the second derivative?
12x squared minus 24.
Yep.
12x minus 2.
Say that again.
12x and then multiplied by x minus 2.
Yes, you could factor it into 12x multiplied by x minus 2, yes. But we're just going to plug these numbers in. So if we test, let's just do f of 3 first. Actually, I like Rachel's way. You said 12x times x minus 2, right? So that'd be 12 times 3 times 3 minus 2.
So that's,
So F-
26.
Uh-huh. Wait, what?
It's
It's okay.
36, sorry.
You see 36, which is positive, which means that F is concave up or concave down? Concave up. Positive, second derivative positive means concave up. Positive is up, negative is down. So concave up, thus f of 3, which was equal to negative, what was it, 27? I can't remember. Is a, so if you're concave up, that number had to be a what? A minimum. So second derivative positive means concave up, means that critical number was a min. What about the second derivative at 0? What's that going to be? Zero. And when that happens, this means the second derivative test fails. And you can make no conclusion.
So I mean, so you don't know if the first one was right or not?
No, the first, then you'd have to revert to the first derivative test.
Oh, okay.
Does that make sense? And then revert to,
So the F of 3 is still true?
yes.
I thought.
And the conclusion should be the same with both tests, right? We concluded it was a min in the first case, it's a min in the second case. Okay, so here's how I could ask you about this. On your paper, but it would be good for me to say, because I could say something like, suppose f prime of 2 is equal to 0. Is this a max min neither if part A, or I guess neither probably is better, inconclusive. What if I said f prime prime of 2 was 7? So you know the first derivative is 0, right? If I said the second derivative was 7, that implies your function is concave up, which implies at f of 2, you have a min, right? Doesn't matter what positive number I gave you. If I said, oh, it's equal to some positive number, well then, concave up, min. What if I'd said the second derivative was, at 2 specifically, was negative 1 over 100? What does that mean about f? Concave down. Concave down looks like this, right? Which implies that f of 2 is a max. Okay? And if I'd said, what if I gave you the second derivative was 0? Oh, shootness. I should say 2 equaling 0, then inconclusive, right? You don't know. It's not possible to tell. Not enough information. Does that idea make sense? That's how I could test that you remembered this thing without actually, because otherwise you could do the first derivative test and you wouldn't have to use this one, right? Okay. Alrighty. So, same thing as before. We did one of these already, but we're going to also talk about the concavity as well. So here's the picture of f prime. When is f increasing? When is f decreasing? So we're not going to make a sign chart this time. It's the graph of f prime. So is f increasing from 0 to 2? So remember that f is increasing if f prime is positive, right? So what does that mean in terms of this picture? We did one like this where you're like, oh, it's really easy. This is true if the graph of f prime is blank the x-axis above. So from 1 to 6, increasing from 1 to 6, and we'll just say 8 to 9, okay? Because the picture does sort of more obviously end, right? Whether or not you include 9, it doesn't matter. Like, it's just not that important. Okay, so that's because f prime above x-axis. It says the hardest thing is going to be convincing yourself that that is not the graph of f. Does that make sense? That's what you're going to do wrong if you do something wrong on this. Where is f going to be decreasing? Which will be from, and 6 to 8. So just watch out for stuff like that. It's not the graph of the f function. Does that make sense? That's the thing to be careful about. Okay. At what value of x does f have a local max and a local min? Local max at x equals local min at x equals. Okay. So this is a place where f prime is 0, right? You buy that? So first your derivative is negative, then your derivative is positive. So what happens at that point? A local min at x equals 1. Where's the next possible local max or min? 6. And f prime is positive to the left of 6, negative to the right of 6, which makes 6 a max. And at 8, negative to positive, making 8 a min. What do you think the most common wrong answer is? Nope. What if you thought it was the graph of f? Where would the maxes be? 2 and 5, right?
7.
And then the mins would be at 3 and 7. Okay, so just remind yourself that,
That's what I started doing.
yep, so that's just tricky. Okay. Okay,
You should put both graphs up there.
no. And what interval is f concave up or concave down? So f is concave up if f prime prime is bigger than 0, right? So looking at this picture, we're looking at the derivative of the derivative, right? This will be true if f prime has positive slope. Does that make sense? The derivative of the derivative will be positive if the derivative of the derivative, if the derivative has positive slope. Okay, did you buy that? So where is f concave up? Where is the slope? Where are the slopes positive for this thing? 0 to 2, that's all positive slope stuff. 3 to 5. And 7 to 8. 7 to 9, sorry. That's a little bit like how when we graphed derivatives, that'd be where the derivative would be above the x-axis, right? Where is f concave down? 2 to 3, 5 to 7. Because f prime will be f prime prime will be negative when f prime is decreasing, right? You write that down. F prime prime negative when f prime decreasing. That's probably the best way to think about it. Does that make sense? F prime prime will be positive when f prime is increasing, right? Oh, holy moly. Let's just finish this one and then we'll do part D and then we'll be done. Okay, state the x coordinates of the points of inflection. So where are they? 2, 3, 5, and 7. Yay. Sorry about that. I didn't even know. So the last part for this one, assuming f of 0 is 0, sketch a graph of f. So what this assumes is that you begin at the origin. I need all my information. Okay, and then our points were 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So what did the function do from 0 to 1? If you look back at part A, what did it do from 0 to 1?
Increase.
I don't think from 0 to 1 it increased.
Oh, decrease.
Decreased. And was it concave up or concave down? Concave, look at part C, it's concave up from 0 to 2. So it decreases to some point, and it's concave up. Okay. And what happens at 2? There's an important thing that happens at 2. What do you have at 2?
Concave down.
It changes to concave down. So you can put that wherever you want. I'm just going to put it up here. It's concave up until that point, and then kind of changes to concave down. But it's still it's increasing from 1 up until when does it stop increasing? Look at part A. When does it stop increasing? 6. So up at 6, it's been, and something happens at 5 as well, doesn't it? I think there's an inflection point at 5. So just remember this, it's concave down until 5, changes to concave up. Do you buy that that does what it's supposed to do?
Wait, where did the taper off?
Where did this thing come from?
Yeah.
Where did that point come from? That came from the fact that when I was looking at my analysis, I saw that there was an inflection point at 5. If you look at part D. So there has to be a point where it goes from concave down to concave up.
Okay. It looks like you put it at 0.4.
Oh, I didn't mean to. It should, did I count wrong? It should be right there. Concave down, concave up. Okay. And then what happens? What's concave up from? Wait a second.
But they're also going to change it at 0.3.
Holy shiznits. Stop. Stop. We're stopping. Back up. Let's color code. One, 2, 3, 4, 5, 6, 7, 8, 9. Okay. That's a problem when I don't have my stuff in front of me. So there are critical numbers where at x equals 1, 6, and 8, right? And there are inflection points at what numbers?
2, 3, 5, and 7.
There we go, that'll help. Okay. So from 0 to 1, f is decreasing, concave up. Do you buy that? Okay. Decreases, concave up. How about from 1 to 2? F is increase or decrease? Increase. And is it concave up or concave down? Concave up still. Okay, next we have 2 to 3. F is still increases. What's different? Yep, increases, concave down. Okay. Okay, then we have from 3 to the next important number is 5. F is still increases, and it's concave up. 3, 4, 5. Okay, increasing concave up. Okay. Oh, 5 to 6. It did a lot of concavity changes. F is still increasing, but it's concave down. Holy. Okay. Where's the next important number? 6 to. F is decreasing, and it's still concave down, right? So it does something like that.
So that was from 6 to 7?
Yeah, but I don't know if I might line them up correctly. I mean, if, so 5, 6, 7, it's not too awful, right? From 6 to 7, yep. And next we have 7 to 8. F is, I think it's still decreasing. Because it decreases from decreasing, and it's now concave up. And I think it's concave up forever now, right? Because it's concave up till 9, so it decreases, but it's concave up. There we go. That question, how you're going to be asked, is going to be, you're going to be asked it in WebAssign, and it's going to say which of the following pictures matches your analysis. And how far up or down you put those points is completely up to you. And the only way we knew we began at 0 is because they told us it did. Yeah.
Isn't from 8 to 9, it's increasing, so.
Oh, man. So 8 was a critical number, wasn't it? Yep. Like that. There you go. Increasing concave up. And still a function, so that part's going to go away. And it won't go away, so I'm going to have to wait it out. Yep. But that one was particularly ugly because it had so many changey points. Oh my God, I wouldn't do anything like that to you in a test. Okay. And the last one, which is the last page. Okay, this thing, you were given a bunch of information and you're asked to sketch a picture from it. So f of 0 is 0, f of 2 is 3, 4, etc. Okay. Okay. So what does f of 0 equal 0 mean? What do you pass through? The origin. How about f of 2 equals 3? Over 2 up 3. F of 4 equals 6 means over 4 up 6. Okay. What does this derivative business mean?
The slope is 0 at x equals 0.
Exactly. Slope is 0 at x equals 0 and 4. Okay. What does this second part mean? What's f doing from 0 to 4? Increasing, does that make sense? And what's happening for less than 0 and bigger than 4? Decreasing. So we're increasing on 0 to 4 and decreasing negative infinity to 0 union 4 to infinity. Does that make sense? Because you're told the first derivative is positive. That's what being bigger than 0 means you're positive. And if your first derivative is positive, your function's increasing. If your first derivative is negative, your function's decreasing. So from 0 to 4, your function's going up. And then on the other intervals, it's going down. And now what does the second thing mean? What's that telling you about?
Concave up.
Concave up from, I think, negative infinity to 2. Does that make sense? And concave down from 2 to infinity. Yep. Okay. Okay. So your first interval is from the left side up to 0, right? From the left side, we'll say minus infinity to 0. Your f is decreasing and concave up. Does that make sense? So you decrease and you're concave up. What about 0 to 2? Increase or decrease? Increase, and are you concave up or concave down? Concave up still. And then how about from 2 to 4? Increasing concave down. And how about 4 to infinity? Decreasing concave down. Forever and ever. So the numbers at which you break those into pieces are the inflection points and the critical numbers. Does that make sense? You say, okay, so from wherever to first inflection point or critical number, am I increasing or decreasing in how? Like concave up or concave down? Yes. Did you have a question, Natalie? Okay, great. All right, and then this one. So this one just involves a little bit of graphing and also using stuff you actually already know. So part A is the only additional thing. Find the vertical and horizontal asymptotes. So where is this guy going to have vertical asymptote? At the denominator equals 0, which is x equals 0, yes. So 1 equals e to the x. That means x is equal to 0. And that would be because natural log of 1 is 0, right? How would you find the HA? Limit as x goes to infinity of this thing. And we had one like that on your test, I believe, right? You had to multiply by 1 over e to the x, 1 over e to the x. That was the limit as x went to infinity of 1 over e to the x minus 1, which is negative 1. So y equals negative 1. And I think this one's actually a teensy-weensy bit tricky. You also have to find the limit. The one that's on your homework isn't this tricky, but you've got to find the limit as x goes to minus infinity as well. So do you remember how we did that? I kind of did it by accident there. Change the x's to negatives and make x go to infinity. Okay, does that part make sense? Now, I think this is actually going to be 0. Here's why. Same thing as 1 over e to the x over 1 minus 1 over e to the x. Do you agree with that? That's what happens when you have negative exponents, right? And so as x goes to infinity, where's 1 over e to the x going? 0. So you're going to have 0 over 1 minus 0, which is going to be 0. So you have 2 horizontal asymptotes. There are 0 and negative 1. So that's a bit trickier than the one in your homework for sure. This one was different. There's a question like this on the homework. Okay, I don't think I'll put one on the quiz. And the homework one isn't even this hard because it's a polynomial that has like x squared in it. It doesn't have e to the x in it. Okay, what's next? So for that, you've got to use the derivative, right? So low d high minus high d low all over low squared. Set it equal to 0. So that's, is it okay if I take up this step and I factor out an e to the x? So I have e to the x times 1 minus e to the x plus e to the x. I think you get this. Is that okay? So if you're solving that equal to 0, you get 0 equals e to the x, which has no solution. Does that also make sense? Now, when that happens, you got to be a teensy bit careful. Technically, x equals 0 is on your number line. And the reason is that at x equals 0, f prime of 0 is undefined. Do you agree with that? And you could have, even though it's not a critical number, you could have some kind of changing happening there. It's possible. So you still do that when you're testing. So f prime's sign. I do believe, though, that this is both positive and then positive. Does that make sense? E to anything is positive, right? And the denominator is positive because you've got something squared, right? So your function f is increasing from negative infinity to 0, union 0 to infinity. You can't include 0 because at 0 this function is not defined. Okay, good God, second derivative. Are you ready? Oh, local maxes and mins. This one's actually easy. There's none. And the reason there's none, there are technically no critical numbers. So this will have no maxes and no mins.
There's no critical numbers
Because the first derivative never equals 0. Yep. Okay, so the first derivative was e to the x over 1 minus e to the x squared, right? Which is the same thing as e to the x times 1 minus e to the x to the negative 2, right? I think it's going to be best to use the product rule. So second derivative is e to the x, 1 minus e to the x to the negative 2, plus e to the x times minus 2, 1 minus e to the x to the minus 3 times almost negative e to the x. E to the x over 1 minus e to the x, the quantity squared, plus, I think it's actually plus.
Oh, yeah.
But, you know, you could have made a mistake. Do you get why plus? Because I have that negative 2, and I have a negative e to the x.
And then negative what?
A negative e to the x, this thing on the end.
Oh, I wasn't looking that far.
Okay. Now what's the last thing you have to do here to simplify this?
Get a denominator.
Mm-hmm.
Denominator
Denominator
thing.
thing, yep.
The denominator.
So that's going to be e to the x minus e to the 2x plus 2e to the 2x over 1 minus e to the x squared. Or goodness gracious. Say that again. Oh, thank you. Yep. Or I think it's e to the x plus e to the 2x. Do you guys agree? Does that make sense? And so this one is definitely trickier than the one on your homework, so don't worry too much about it, but because the devil's in the details in this one. If you can take out an e to the x in the numerator, does that make sense? So that's the same thing. The one in your homework will be easier because it's going to be a polynomial. It's not going to have e's in it. Just have to pick a different problem. So holy God, where is this 0? It actually isn't 0 so many places, is it? I don't think it's ever equal to 0. No. So f prime prime does not equal 0 ever. So the only number you put on there again is 1. That's that whole undefined point. No, shoot. Where was the undefined point? X equals 0. And then the sign of f prime prime is, ooh, I think this might actually be different. If you were to plug in something like, maybe not though, -1, I think it's still positive. Plug in something like 1, I think that might now be negative. Do you agree with when you plug in 1, you get a negative? Because the denominator becomes negative in that case, right? 1 minus e is negative something, right? Because e is about 2.7. So your concave up from negative infinity to 0, concave down from 0 to infinity. Are there any inflection points? Technically not 0. Well, because 0 is actually a asymptote. But you know what I mean? 0 is not a defined point. Okay, is there another part to this? Did I say to graph it too?
Yeah.
Oh man. Okay. So you have a VA right there, right? And you have 2 HAs. You have one here. You also have one at 1, don't you?
-1.
Oh, yes, -1. Thank you. Okay. Okay, so we were, what was the increasing, decreasing? Because I don't have it written down. So when you look back at your first part, where were we increasing, where were we decreasing? Because it was like all 1.
From -infinity to 0, and also increasing from 0 to.
Okay. And how about and there was no decrease, how about the concave up?
From -infinity to 0.
And concave down?
0.
Okay. So if we're increasing and concave up, and also it was the limit as x went to positive infinity of the function, that was equal to -1, right? And the limit as x went to was equal to 0, right? This just seems sort of like not what I expected. So increasing concave up. Does that make sense with the analysis we have? Okay. Now we need to also increase, oh, okay, I got it. Also increase but be concave down, right?
Yes.
And we have to approach -1, I think we have to do this kind of thing.
Oh,
A good way to convince yourself that that would be true would be to plug some numbers into this and make sure you get negative things. Use a grapher to make sure that you have it right. This one was way trickier than I intended it to be. Okay, so that's all. But the point was